In this video, I'm going to do some demonstrations of the derivatives of exponential functions. So first, here's the basic derivative rule. The derivative of the natural exponential function is itself. So d over dx of e to some u is e to the u times du over dx. So the e to the u part here happens because the derivative of the natural exponential function is itself, and then the du over dx part happens because of the chain rule, because normally we have e to something more than just an x. Okay. Let's work a few examples. So here's the first one. F of x equals e to the 3x. Okay, so here we go. There's a reminder of the derivative rule. The derivative of e to stuff is e to stuff times the derivative of stuff. So there's f of x equals e to the 3x. F prime of x, I'll begin by just writing that it's the derivative with respect to x of its formula. I'm writing it nice and big because I want to make it clear we're looking at the derivative of e to a power. So when I match this up against the rule, the stuff here is 3x. Okay, so let me write this out. F prime of x equals, okay, I'll write these pieces out. E to, and the stuff is 3x, times the derivative of the stuff, 3x. So again, that's the exponential rule first that gives us a copy of the thing, and then the derivative of 3x is from the chain rule. Well, derivative of 3x, what do you think that is? 3. Okay? And for basically aesthetic reasons, it's typical to put the factor of 3 on the left and write this as 3 e to the 3x. So it's sort of uncomfortable. Why in the world would you sort of leave the exponential part unchanged? But that really is the correct rule. For f of x equals e to the 3x, the derivative f prime is e to the 3x times 3, or 3 times e to the 3x. Now, I'm going to do an example here. This is related to exponential growth. It'll take me a moment to explain what you're looking at. So first, q equals q sub 0 times e to the kt. Let me explain what all of these symbols are. So q here is some growing quantity. Hence the q. And t is time. So I think of q as being the independent variable and t as being, no, I said that backwards. Q is the dependent variable and t is the independent variable. Now q0, all right, q sub 0 is a constant. So let me do this in blue. Q sub 0 equals the value of q at time t equals 0, and it is a constant. Likewise, this k is a constant, so k is a growth rate constant. Kind of like the interest rate in the continuously compounded interest formula. So if you remember, that was A equals P times e to the RT. The formula here is essentially the same thing as continuously compounded interest, just with different letters. So let me actually, I'll just copy this and work with it down here. Okay, dq over dt, I'll use Leibniz notation, is d over dt of the formula for q. So I'll just copy that over here. Now, if you look at this, you should see, okay, there's e to a power, so we're going to need the exponential rule. But be careful not to jump the gun. There's another operation, there's multiplication here that happens after the exponent. So that means we need to handle that first when we do the derivative. This is the easy case of the product rule. This is the constant multiple rule, because we've got multiplication, but one of the things that we are multiplying is a constant. So we only need the first half of the product rule. I'm actually going to just copy that so that I don't have to fiddle with changing the colors like this. Yeah, let me copy this as well. So that's the constant multiple rule. The constant times the derivative of the rest. If you did the full product rule, you would end up with the derivative of q0, which is 0, times e to the kt, because this again is constant. But since we really don't need to do that if it's multiplied by 0, we'll just leave it out. Okay, now we have an unfinished derivative, the derivative of e to the kt. I will keep the q0 that we already had. We keep it because it's multiplied. Then again, I've got derivative of e to stuff. So I need to write down e to the stuff. Yeah, all right, I'll make that blue. Times the derivative of the stuff. And that happens because e to the power is the amazing indestructible function. It is its own derivative. There's one operation left, which is this constant k times t. So again, we'll use the constant multiple rule. We'll keep the k. So let me copy all of this. We'll keep the k because it's multiplied. Ooh. Oh, I love technology, don't you? We'll keep the k because it's multiplied. And now it's big enough to move. Okay. And then the derivative of t, well, that's easy. That's just 1. And usually we don't even write times 1. Okay, so there we go. dq over dt is q sub 0 times e to the kt times k. And if you wanted to, you could clean this up a little bit. It's traditional to put the constants out front, constant factors out front, and there we go. Now, we were also asked to compute derivative of q with respect to t and then divide it by q. So if you're looking at the slideshow, that's this part over here. We were asked to look at that. Here's why. dq over dt divided by q is, I'll copy from up here what dq over dt is. And then for q, I'm going to go back to its formula, because remember, q is a dependent variable that depends on t. And what you should, of course, see is that we have factors that cancel. There's a q0 multiplied in the top and the bottom. There's also an e to the kt multiplied on top and bottom. So when you clean all of this up, the denominator is now 1, so we don't even need to write it. But now we have dq over dt divided by q equals k. Now, what is the significance of this? The first is that this thing on the left is a relative rate of change. So let me do this. This is a relative rate of change. Relative rate of change of q with respect to t. This particular book doesn't go into much about relative rates of change, but it's very closely related to the concept of an interest rate, right? An interest rate of, say, 5% means that the amount added to something is somehow related to 5% of what's already there. So if you take a quantity and ask, how much are you changing it by compared to how much is already there? That's a relative rate of change. The fact that this is a constant is significant. An exponential function, so an exponential function of the form q equals a constant q sub 0 times e to the kt has a constant relative rate of change. Just to put this into perspective, let me come over here and write note. A linear function, so I'll write this as y equals mx plus b, has a constant rate of change dy over dx equal to just the slope m. So a linear function has a constant instantaneous rate of change, a constant derivative. A linear function has a slope. It's the same slope everywhere. An exponential function like I've drawn over here has the property that it has a constant relative rate of change, which is, something a little different. And that constant relative rate of change is actually the k from up in here. Another consequence of this, let me rewrite this as dq over dt over q equals k. I can multiply both sides of this, and let me do this in this color, by q, and cancel out the q there, and get that dq over dt is k times q. This is a differential equation, and it's one of the most important ones because it's not trivial to solve it, but it's relatively easy. Most differential equations cannot be solved. What makes it a differential equation is it says that the derivative of q depends on the value of q. In particular, the rate at which q is changing is proportional to the amount of stuff that's already there. Again, this is related to continuously compounded interest. It's also related to exponentially growing quantities. If you put bacteria in a nutrient solution and just let them go, they will grow exponentially. The spread of an epidemic is initially exponential as well. That's because the number of new cases is proportional. So the number of new cases in a given time period is the rate of change of the total number of cases with respect to time. The number of new cases is proportional to the number of cases that already exist, because new cases come from susceptible people making contact with infected people. Okay, so I will not be asking about differential equations on tests, but just given the context of this video, I thought it was important to mention this and just sort of show you the connection between rates of change and exponential functions, and how, again, the distinction here is that a linear function has a constant rate of change. An exponential function does not have a constant rate of change, but it does have a constant relative rate of change. Okay, here's another function. If you've taken statistics, you might recognize this. This is part of the density for a normal distribution. G of t equals e to the negative of t squared over 2. I should warn you at this point, don't try to squeeze things into a single line of notebook paper. There's plenty of space, and when you have an exponent with a fraction and another exponent in it, make it as big as you need. Let me, as a matter of fact, just really exaggerate that and write it nice and big and draw in the order of operations boxes. Okay. Now, we don't usually draw them in, but just like the top and bottom of a fraction are groups as if they were in parentheses, the stuff up in an exponent is effectively in parentheses. So within this structure, there's an exponent, there's division, and then the multiplication by, well, yeah, the negative there is effectively multiplication by -1, and then finally, the very last operation is e to the power. So that means that when we do g prime, we will actually start with the exponential rule. Before we do that, though, I'm going to do a little bit of rewriting that usually helps. I'm going to, let me come over here and write it out. What I'm going to do is spread out the t squared over 2, and you do that by making it two separate fractions and putting one in the numerator and denominator, and then I'm going to get rid of that division by 1. So I can think of t squared over 2 with a minus sign in front of it as effectively -1/2 times t squared. So over here, I'm going to write -1/2 times t squared. And this step is just algebra. When you're good enough at algebra, you won't even need to write that out. It'll just come naturally. So again, let me write out, I'll use d over dt since t is the independent variable in this function. Derivative of e to the stuff is e to the same stuff times the derivative of the stuff. This time, the stuff, let me make this a little bit bigger here, this is all the stuff. So when I write out the derivative, g prime of t is, well, I guess I can write it over here, e to the negative 1/2 t squared, I may as well write it like that, t squared, times the derivative with respect to t of negative 1/2 times t squared. Okay. Now I'm going to copy the part that we're already done with. The derivative of negative 1/2 times t squared, what is that? We keep multiplication by negative 1/2, and then the derivative of t squared is 2t. Okay, so that is the derivative of e to the negative t squared over 2. At this point, we should do a little bit of cleanup because, well, we've got a lot of multiplication. So if you look at this, we've got e to this negative 1/2 t squared times negative 1/2 times 2 times t. It's, first, it's possible to cancel the 2's. And then I might as well move this multiplication by negative 1 and t up to the front. Again, it's basically just because it looks better that way. And if you're careful, you can write that as e to the negative 1/2 times t squared like that. You're also free to put the t squared back up over the 2. So there you go. That's the derivative of this function. Pause the video and take a few minutes and try to solve for the derivative of y with respect to x. Well, I guess solve isn't the right word. Just evaluate the derivative of y with respect to x. Something to know is that the capital A is a constant. So you should treat it as if it were 5 or 13 or 2.86509 times 10 to the negative fourth. Just a constant that I didn't want to keep writing down. So pause the video and see if you can work out dy over dx. Okay, here is our function. Again, I'm going to draw in the structure from the order of operations. Now we have a fraction. Within the fraction, we have a top and a bottom, and those are grouped. But even deeper than that, we have exponent with stuff inside. So the stuff, oh, erased too much there. The stuff in here happens early. This is the deepest layer, negative a times x. So that's inside that group. Then the exponential happens. Then the 1 plus happens. And then finally, we do this division. So that means that, yes, we will have to deal with the exponential rule sooner or later, but we don't start with it. What rule should we start with? Yeah, we should start with the quotient rule. Now, there are other ways to do this, but the quotient rule will it has the advantage that what we get at the end is all already over a denominator. So here we go. Top is 1, and the bottom is 1 plus e to the negative a times x. Derivative of the top is easy. What is the derivative of 1? 0, because 1 is constant, and just a constant. Now for the bottom, take a moment and give that a try. Okay, first, it's easy to miss, but we've got derivative of 1 plus. Normally we wouldn't even bother to write this, but since we're getting practice with this new rule, I thought I would. Derivative of plus a constant contributes plus 0. Normally we don't write it, but I'm writing here tonight because we've got a lot of stuff going on. So now we're at this stage. I'm going to write out, just for the moment, derivative with respect to x of e to the minus a times x. So there you see e to the power derivative of e to the stuff is e to the stuff. And there's the stuff. So we have e to the negative a times x. And then we have to multiply by the derivative of the stuff. And just remember, right, that negative a times, that's multiplication by a constant. We keep multiplication by a constant. So e to the negative a times x times, and this becomes negative a times 1, if you like. But usually we don't bother writing times 1. And finally, we can do a little cleanup. Negative a times e to the minus a times x. Okay. Now, where were we going with all this? We are in the process of doing the quotient rule. So here we go. Quotient rule. dy over dx equals, I need the derivative of the top times a copy of the bottom. Well, the derivative of the top is 0, and it really is 0 because it was the derivative of a constant and nothing else. So I really don't need to even write times bottom because it's just going to get zeroed out when we start cleaning stuff up. Then we subtract, and we subtract the top times the derivative of the bottom. So 1 times, and the derivative of the bottom, I'll copy that into place. Then we have to divide the whole thing by the square of the bottom. So that is the result of the quotient rule. We are now finished with all of the derivative operations. All we have to do now is a little bit of cleanup. Here we go. dy over dx equals, okay, here's a couple of things that happen. Let me actually just copy this so that I can, let me just do that, copy that. So first, this just becomes 0. Next, we don't really need to write times 1, so I'm going to gray that out. And at this point, if you notice, we have negative of a negative cluster of factors. So I don't really need that. I can do a double negative simplification, and at that point I can gray out some more stuff. And here's what we're left with. dy over dx equals a times e to the minus ax over 1 plus e to the minus ax as a group squared. I should give you a little bit of explanation for why anyone would want to use a function like this. This is something called an exponential sigmoid. And this particular one, if I draw the axis like that, its graph looks like this. So it has a horizontal asymptote at 0 on the left, and it has a horizontal asymptote at 1 going off to the right. This is used for a lot of different things. In particular, when a population starts growing exponentially, but then starts to run into a ceiling, starts to run into resource limitations, very often it will grow in the shape of a sigmoid. And if you look at data about the COVID-19 epidemic, for example, you'll see it doesn't quite look like this, this exact function, but it's roughly that shape. Okay, so let me show you one last problem involving the derivative of an exponential function. I'd mentioned a couple of times that there are reasons related to calculus why e, of all things, is the natural number to use as a base for logarithms and exponential functions. Now I'm going to show you why. So y equals 2 to the x. In order to apply our derivative rules, the base has to be e. Any other base isn't going to work. So we need to rewrite this function using e to a power instead of 2 to a power. Now how are we going to do that? We're going to need to do some algebra. The first step is to apply ln to both sides. Okay, so I have y equals 2 to the x. I'm going to apply the ln function to both sides. And again, I am not multiplying by ln. ln is a function. It isn't a number by itself. ln applied to a number results in a number, but ln is a function. So we are not doing multiplication. Next step is to take apart the right-hand side of this. So I'm going to leave ln of y the same. If you look at the right-hand side, I have ln applied to a base to a power. Remember, there's an ln property that lets us take apart ln applied to a base to a power. So do you remember how that works? We'll get a factor from the power times ln of the base. Okay, so that's so far just algebra. Now I'm going to do something a little bit strange. I'm going to apply the natural exponential operation to both sides. Okay, so I'm going to do e to the left equals e to the right. Okay. Let me copy the left and copy the right. Okay. I'm now going to simplify on the left. Remember, e undoes a logarithm. E to the power undoes the logarithm. And that takes us back to y on the left. And on the right, I'm going to leave this as e to the, well, at this point, let me put this in more usual order, ln of 2 times x. So all I have done is to rewrite 2 to the x using several steps of algebra. This is the same function, but a different expression for it. And if you like, you can convince yourself of this. Try plugging in a few values, maybe 3 or 4 or 5 for x, and convince yourself that 2 to the x agrees with e to the ln of 2 times x. Okay, what next? Now I'm going to do the derivative. So dy over dx is derivative with respect to x of e to the ln of 2 times x. Okay. The thing that we are taking the derivative of is e to a power. So we use the exponential rule and the chain rule. The exponential rule says that the derivative of e to a power is, well, it's e to the same stuff. So that's the exponential rule. And then the chain rule says that we multiply by the derivative of the stuff. Now at this point, there's something that's very easy to be confused about. We're going to take the derivative here in this chain rule part, but look very carefully at this ln of 2. There we go. ln of 2 is a constant. ln of 2 is approximately 0.69. It is a constant just like 4 or 11 or 2/3. Even though it has an ln in it, it's a constant because it does not depend on x. ln of 2 is always 0.69. It does not matter what x is at the moment. ln of 2 is always the same. What we are looking at here is a situation where we need the constant multiple rule. Because we are multiplying the constant ln 2 times the independent variable x. Okay, so what happens? Well, there's all of this stuff that we've already handled. I'll just copy it into place. Derivative of a constant times x. What is that? It is just the constant, and if you like, you can multiply by 1 for the derivative of the x. But usually we don't bother. Okay. So notice that the ln of 2 is not turned into 1/2 because the derivative of ln of 2 would be 0. It really isn't worth going to the trouble of trying to do the logarithm rule and the chain rule on a constant. That's a place where students often get confused. If it was ln of x, then we would start seeing some reciprocals. But since it's all a constant, all we see is ln of 2. Now, there's one last thing we can do to clean this up spectacularly, and that is to recognize that this e to the ln of 2 times x is familiar. It's actually y. This happens all the time when you're doing exponential functions and derivatives, because the derivative of e to stuff is e to stuff. So the derivative of a function that has an e to stuff component is going to have copies of that e to stuff. And importantly, where that came from was this 2 to the x. So in other words, 2 to the x is actually equal to e to the ln of 2 times x. So down here, where I recognize an e to the ln of 2 times x, I can, if I like, turn that back into 2 to the x. So part of what's going on here is that if you wanted to do a general exponential rule, a general exponential derivative rule, you would say that if f of x is b, well, yeah, is b, let me do it like this. Let's say y is equal to b to the u. Then dy over dx is b to the u times a constant factor ln of b, then times the derivative of u. Sometimes you'll see that in tables with derivative formulas and sometimes not. This is the reason that e is the natural base to use. It's because if you try this with e for the base, ln of e is 1. And so this part doesn't come into play, it's just 1, and we don't even normally write times 1. So there you go. That is the derivative of 2 to the x. Just as one last little thing here, I'm going to show you the relationship between the derivative rule for the logarithm and the derivative rule for the natural exponential. So here we go. Y equals e to the x. I'm going to take the logarithm of both sides. On the right, ln undoes e to the x and leaves just x. Now I'm going to take the derivative of both sides with respect to x. This is going to be a little funny looking at first. I get 1 on the right because the derivative with respect to x of plain old x is just 1. But now I can do this. Derivative of ln of stuff is 1 over the stuff, which in this case is y, times the derivative of the stuff, which is dy over dx. So what I've just done there is the logarithm rule and the chain rule combined. Now I can multiply by the y and get dy over dx equals y. And what you are seeing is that dy over dx is e to the x. So in other words, because the derivative of the logarithm is the reciprocal, this calculation shows that this inverse relationship between the logarithm function and the exponential function forces e to the x to be the amazing indestructible function. So there you go. That's why these derivative rules have to be the way they are, and e is the magic base that has all of these nice calculus properties.